Good afternoon, everyone. Maybe if we make start. So for our final talk of the day, we have Hao Ni from UCL. She'll be talking about a high-rank path characteristic function, which is an approach for learning the filtration of stochastic processes. Thank you.
Thank you very much for the invitation and the introduction. It's my great pleasure to be here and talk about our recent work on high-rank path characteristic function of the stochastic process and its application for synthetic time series generation. So let me start with the motivation of our work. The application of GAN models for the synthetic time series generation is challenging. First of all, the GAN models are known to be difficult to explain and also computationally expensive due to its min-max nature. For the time series data, this issue becomes more severe due to the potential high dimensionality and the complex spatial temporal structure. Moreover, in contrast to the static image generation, the synthetic time series generation lacks the systematic evaluation framework. Our work focuses on to improve the quality of the discriminator by incorporating the principled mathematical representation for the time series distribution through the rapid theory. So throughout my talk, I will not distinguish the discrete time series and the continuous time series. So in practice, we often observe the discrete time series, and we will embed it into the continuous path space by linear interpolation. By doing so, it provides the uniform treatment for time series of possible irregular sampling and variable length, and also the continuous time perspective of treating discrete time series is more suited to the high frequencies of data. The question about how to design the effective discriminator for the time series generation actually boils down to two key mathematical questions. That is how to represent the stochastic process, and second is how to quantify the distance between two stochastic processes. The distance between two stochastic process can be defined in the weak topology sense. Here we can view the stochastic process as a path-valued random variable. However, this viewpoint may lose some information about the stochastic process. In the other words, that if the two stochastic processes are close in the with distributional sense, it doesn't guarantee that its conditional law are close in general. And in the slides, I provide you with an example in the literature which illustrates this point. So on the left-hand panel, you can see the sample plot of the process XM. This process only has the two possible scenarios. It's either the 1 plus 1 over n and 2, or the other possible scenarios is 1 minus 1 over n and 0. And each scenario has the equal probability. And the another process X is defined in this plot. So it also has the two possible scenarios, either 1 by 2 or 1 by 0, with equal probability. So the transition probability is shown in the figures. And it's very easy to see that Xn will converge to X in the distributional sense. However, the conditional law of Xn, given the filtration information F1, will not converge to that of X. It's very easy to see at t equals to 1. So for this process Xm, what happened at stage 2 is deterministic for all possible n. So when take the limit, it cannot converge to this conditional law of X given the information of F1. That's the random variable with equal probability. And then it actually also can show that if we use xn and x as a certain underlying process, and calculate the corresponding American option price, the corresponding price of xn will not converge to the counterpart of x as well. So it demonstrates that if we made the slightly error models in the past distribution, it may cause a significant loss in the multi-period decision process. So motivated by this example, we would like to construct the discriminator of the GAN model that can effectively capture the filtration information or the evolution of the conditional law of the stochastic process. So to this end, we propose a high rank path characteristic function distance between two stochastic processes. Our approach is based on our prior work, the path characteristic function, which is a faithful representation on the path valued distribution. And we show that the desirable properties of the high rank TCF distance, which are relevant for the generative modeling. Moreover, we designed the effective algorithm for the application of such distance in both hypothesis testing and the GAN models for synthetic time series generation, and validate its performance in comparison with the strong baseline. So this is a joint work with my PhD student, Jia Tao, and my collaborator, Cheng Liu from Shanghai Tech University. So here, let's consider D-dimensional stochastic process X, and the filter process is the underlying process X with the filtration information. The key object to understand this filter process is through the prediction process, denoted by x hat. Well, x hat at time t is defined as the conditional probability of x given the filtration information ft. And here you can see that for each t, x hat t is a measure on the path space, and we are interested in understanding the distribution of such measure valued on paths. And here we call that the sequence of the filtered process xn converge to another filter process x in the extended weak convergence if the law of the prediction process x hat n converge to the law of x in the weak sense. Before diving into our high rank TCF the measure on the path space, let me first recap what is the path characteristic function and why it serves as the nature generalization of the classical characteristic function for the RD valued random variable. So to answer this question, to this end, the key question we need to answer is how can we extend this exponential map for the variable x is a path. Actually, the raw path theory provides an answer to this question. So here, that is the unitary development of the path. Here, that capital UM and the small um denote the unitary matrix group of degree m and its Lie algebra, respectively. So suppose that we have a continuous path of bounded one variation. And let capital M denote the linear map, which map from RD to the Lie algebra U of M. So capital M serves as a role as this lambda in this exponential mapping. The unitary feature of x on the M is the solution to this linear control differential equation, and with the initial condition. And the resulting solution YT always lives in the Lie group. And we call that the solution Y at the terminal time is the unitary feature of the path x on the M. So let's have a closer look at this object. So when X is a linear path, the unitary feature can be calculated explicitly. It's nothing else but the matrix exponential of M applied to the increment of the path X. And when M equals to 1, the Lie algebra U1 is the set of all pure imaginary numbers. Then we can see that the unitary development map is reduced to the classical exponential map, which is shown in the classical characteristic function. And we call the map which maps from this linear from the whose images UM to the unitary development of X as a unitary feature of X of the order M. And we can show in the literature, it has proved that the unitary feature of X of all orders can determine the unparameterized path X uniquely. Moreover, the unitary feature enjoys the multiplicative property. So if you have the two paths X and Y, the unitary feature of X concatenated with the path Y is the product of the unitary feature of X and the unitary feature of Y. So this property allows us to calculate the unitary feature of any piecewise linear path explicitly. In our previous work, we constructed the development layer based on the unitary feature. This layer takes any piece, the discrete time series X as the input, and the output is a unitary development, while the model parameter of the development layer is a linear coefficients of this linear map M. The development feature of the discrete time series can provide effective feature representation of the time series because in practice, we can train the linear map based on the data and the utility of the task to optimize the linear map, and the resulting unitary feature is a finite dimensional feature representation. So then when the underlying process X is the stochastic process, it's natural to define the expected unitary development as the path characteristic function. In fact, that it has been proven in the literature that if we have the two paths valued random variables X and Y, then the lives in this path space with certain regularity condition, then those two path value or random variables have the same law if and only if their path characteristic function are the same. So here you can see that the path characteristic function PCF can determine the distribution on the paths uniquely. However, as shown in the first toy example, it doesn't necessarily imply that it would determine the filter process uniquely. So to this end, we propose a high rank PDF of the stochastic process to capture the filtration information. So the goal is to find the good representation to summarize the distribution of the prediction process X hat. And the first observation is X hat at time t is the distribution on the path space, but it's conditional probability. So we can use its PCF to represent this conditional distribution. And for each given linear map M1, the PCF of the prediction process X has T evaluated at M1 induces the matrix value stochastic process. And again, it can be characterized by its PCF. So I gave the virtual illustration of this. Yeah. So we start from the stochastic process xt. And so we consider x hat t by we consider x hat t as the conditional law of x given the filtration information. And for each x hat t given the linear map M1, we can calculate, we can get the this conditional expected development, which is a matrix value, and that is resulting this matrix value is the stochastic process. And again, if we give another linear map M2 and calculate the corresponding expected development, it will result in the final matrix value to output. And indeed, that's how we define the high rank path characteristic function. So it's a mapping which maps from the admissible linear map pairs M1 and M2 to the expectation of the unitary development of this expected development process. And we use a superscript 2 to indicate that we actually take the expected development twice. And once we have this high rank PCF, we can use it to define the distance between two stochastic process. So instead of to consider the fixed M1 and M2 in the definition of the high rank PCF, before we now consider the random linear map, this board M and this curl M. So the distance of this high rank PCF, the distance associated with those two linear maps is defined between the two filter process X and Y is defined in this way. So the square of this distance is given by the expectation of the distance between high rank PCF of X and Y respectively, and evaluated with this two linear maps. And the expectation is taken under the distribution of those two linear maps. And here you can see that if the two filter process has the are the same in the extended weak topology sense, then this distance will equals to 0. And we can actually construct the distance of the metric based on the high rank PCF distance to ensure that if we have the sequence of the filter process Xi converge to the filter process X in the extended weak topology sense if and only if this metric converge to 0 under the regularity condition. We are also able to establish the other theoretical properties which are relevant for the generative modeling. That is this high rank PCF can separate points and it has a characteristic. Moreover, it has a uniformly boundness. So the first two properties provide the theoretical justification about the discriminator of the time series distribution to capture the filtration, while the last property is useful because that means if we use this PCF distance as a discriminator in the GAN modeling, we don't need to add the gradient constraint for the model parameters of the discriminators. As you can see that if we have the faithful representation on the distribution on the path space, we actually can apply it inductively to construct the high rank counterpart. Apart from the path characteristic function, expected signature is also useful transformation on the path value variable. And you may hear about the expected signature in the previous talk by Terry Lines. However, intuitively, expected signature plays a role as the moments on the path value random variable. And the expected signature determinant law requires the regularity condition regarding the decay rate of the expected signature. However, it doesn't need for the path characteristic function. And there is a close link between the PCF and expected signature. Intuitively, you can regard the PCF as a generating function of the expected signature. By varying the linear map, the PCF encode all the information about the expected signature. However, it provides the benefit regarding the dimension reduction, because we make this linear map M trainable, so we can choose the more useful M based on the data and the utility. The resulting PCF feature usually leaves a much lower dimension than the truncated expected signature. The high rank signature approach has been studied in the literature before. For example, also the application for the hypothesis testing, distributional regression, as well as optimal stopping problems. However, it's not yet used for the generative due to the computational bottleneck. So in the following, I want to talk about how we propose the efficient numerical method to train the high rank PCFD distance and the application for the GAN model for synthetic time series generation. So to compute high rank PCF, the core question is to estimate the conditional expected development of your process given the filtration information FT from your time series data set for any given M. So we formulate this problem as a regression problem. Well, the input is the path, the time series x from 0 to capital T, and the output is a sequence of unitary development of x from small t to capital T. And because we want to learn this conditional expectation, therefore we regard it as the least square optimization problem. And the regression model we used which should be adaptive. So here for simplicity, we in the numerical examples, we use a two-layer LSTM. So in principle, we need to use adaptive autoregression model to ensure there is no information leakage. Then we can use the gradient descent method to learn the regression module. And to optimize the random linear map M, in practice, we use empirical measure to approximate those the pairs of the linear maps M by the finite samples. Then the corresponding HP high rank PCFD distance is reduced by this average. And for the generative model for the time series generation, you can imagine that we will use this trainable empirical HPCFD distance as a discriminator. So here is we would optimize those linear map to maximize this distance between the true time series data and the fake time series data induced by the generator. In principle, one can do the joint training to learn this random linear maps in one go. However, it's not feasible in practice. So we employ a two-stage procedure to do the training. So first of all, we will learn the linear map for the rank 1 process. MK1 by maximizing the PCFD distance between true and fake data. Once we learn the optimal linear map star K1, we will frozen it and apply the regression model to learn the corresponding conditional expected development, which will be used to compute HR rank PCFD distance. Then we will optimize the linear map of the rank 2 process by maximizing this distance. So in the following, I'd like to show you the application of our high rank PCFD for both hypothesis testing and also the generative modeling for time series generation. So here we consider the task of hypothesis testing of the three-dimensional fractional Brownian motion with various Hertz parameter. And we considered the two sample test. So the samples, the two data sets can be sampled either from the same fractional Brownian motion or sample from either fractional Brownian motion and the Brownian motion. And we will use a permutational test to estimate whether those two samples come from the same distribution or not. And the permutational test depends on the distance we choose. And to assess the performance of the our method, we consider the test power, type 1 error, as well as the training inference time comparison. And the baseline distance we consider include the signature MMDs, the high rank counterpart, as well as the classical vector MMD distance. Moreover, we compare the high rank PCFD with the rank 1 vanilla PCFD distance. So this is a summary table of the test power comparison. And here you can see that the PCFD based method consistently and significantly outperforms the signature MMDs. And in particular, among the PCFD based method, so when the H is close to 0.5, higher rank PCFD improves the performance. And also you may note that the high rank signature MMD might not improve the performance on this example. The reason for that, I think, is because the challenge in estimating this conditional expected signature, estimating the conditional law of the process given the filtration information. And also, in terms of inference time analysis, the PCFD-based method is more efficient than the signature MMDs. That's not surprising because signature MMDs uses the kind of method which is quadratic. The inference time is quadratic in terms of the sample size, while the development-based method is linear in sample size. So it's the PCFD-based method is more suitable for the large data set. And this is a visualization of the PCFD distance. The comparison of the histogram of the distribution of the distance under the null hypothesis and alternative hypothesis. So under the null hypothesis, that means that the x and y should come from the same distribution. So if the histogram is close to 0, it means it's a better performance. And under H1, that's the alternative hypothesis. So the distance is supposed to be away from 0. And here you can see that high rank PCFD distance is more effective to capture the discrepancy between the Brownian motion and the fractional Brownian motion with Hertz parameter 0.475. And the second type of application example is the conditional time series generation. So here we consider the two data set. One is a synthetic data set that is a fractional Brownian motion with a discretization time steps equals to 11. While the other data set is the 5-dimensional, is the stock data set. And with we constructed the time series of the length 10 using the moving window. So the task is to construct the conditional time series genetic model to simulate fixed samples to mimic the conditional law of the future time series given the past time series. And both future time series and past time series have the length 5. And to benchmark our method, we consider the GAN model baseline specific for the time series data, that is RC GAN, time GAN, and also our PCF GAN. So to validate the performance of the synthetic time series generation, here we actually consider the comprehensive list of the test metric in terms of the fidelity, utility, as well as the diversity. That including the discriminative score, sigma-MMD distance, predictive score, and various statistic-based scores, such as how in terms of fitting of the autocorrelation, cross-correlation, as well as the conditional expectation. And for the stock data set, we also consider a test metric in terms of the fitting of the American option pricing. So this is a summary table of the test metrics for across all the models. And you can see that our proposed GAN model shows the outperformance. In particular for the conditional expectation-based score, as well as for the stock data for the American option. And we also visualize the sample plot of the conditional law of the conditional law of the process given the filtration information everything. So on the top row, you can see that the sample plot comes from the ground truth fractional Ryan motion by simulation. And each row represents the sample plot from the different model. So here you can see that our model produces the sample plot which is more closer to that of from the true model. And this is a visualization of the sample plot for the stock data set. So in summary, we propose a high rank PCF that can determine the law of the prediction process and capture better the filtration information of the stochastic process. And we are able to establish some theoretical properties of the proposed high rank PCF and the corresponding distance. Moreover, we designed the inductive algorithm for the hypothesis testing of the stochastic process, as well as the synthetic time series generation. In terms of future work, the current theoretical statement is built on top of the underlying process, is the discrete stochastic process. It would be interesting to extend it to the continuous stochastic process. Moreover, we would like to understand the impact of the price of the network on the performance of the data generation. Moreover, there is still a lot of room to improve for the estimation method for this conditional expectation in terms of accuracy and training stability. For example, it's quite interesting to understand whether we can leverage both the generator and the regression module to build the better GAN model for synthetic time series generation. So I think I'd like to stop here for now. And if you are interested in doing more work about my research group, there is a link here. Yeah.
Are there any questions?